we have an intuition of this time that it's the same for all of us. So we're all in the now, and then a moment later we're all in the next now, and then the entire universe just changes in time. Well, that's wrong. It's simply wrong. There is no sense, there's no well-precise sense in which we can say what is happening now far away. And to make sense of time, we have to think locally. Everybody has its own little time, so to say. Space and time being curved, and Einstein understanding of space is enormously surprising, but quantum mechanics is much more surprising. It was a much bigger discovery about nature. Nature works in ways that are remarkably far from our intuition, in a much more radical and violent way. I find peace exactly in this idea that our obsession with final truth, certain certainties, getting to the bottom of everything once and for all, it's illusory. It's a dream. It's a silly dream.
Hello, everyone, and welcome back to Chasing Consciousness. So in this episode, we have the non-linearity of space and time to get our heads around. Now, in episode 28 with physicist Paul Davies, we talked about the implications of Einstein's work in this regard. And in this episode, we're going to delve even deeper into relativity, particularly of time, but also of space and extension. And that's a subject that our guest today has worked on extensively, Professor Carlo Rovelli. Carlo Rovelli is a theoretical physicist who works mainly in quantum gravity research, heading up the quantum gravity group at the Centre de Physique Theorique in Aix-Marseille in France. And he's also passionate about the philosophy and history of science, so he's a perfect guest for this show. Now, Rovelli has written many popular science books, including the bestseller The Order of Time, which we'll be focusing on today. We're also going to discuss today the release of his new book, Helgoland, which champions his favorite relational interpretation of quantum mechanics. And being such a philosophical scientist, I'm also going to be asking him about intuition, Buddhist philosophy, and psychedelics. Now, a quick reminder, listeners, that all the books, quotes, and scientific papers and concepts and conversation points are always exhaustively included in the show notes, should anyone want to go and check the authority of the research and the ideas that we're citing here. And it's all on the website, should you be unable to find them all. Quite often, I can't fit them all in on the platform. So please use the website. I'm a real stickler from well-referenced claims. And also, a quick thank you to all of you for your support on the project so far. We're growing exponentially. Keep spreading the word by sharing the shows with your friends. Give me a 5-star rating on iTunes or subscribe with the bell on YouTube. All of that is a great, great help to get this in front of new listeners. Also, please follow the show on Instagram and Facebook to be kept informed as the new shows come out, and keep feeding back to me with guest suggestions and your take on the ideas that we're discussing here on the show. Now, Rovelli's unique take on the nature of time is not without controversy in physics, so I really can't wait to get into this. So without further ado, let's go. Professor Carlo Rovelli, welcome to Chasing Consciousness. Thank you so much for coming on the show. How are you?
Thank you, Freddie. I'm very well, and I'm very happy of this invitation.
Well, thank you for being here. It's an extreme honor. Now, Carlo, I always love to start by asking my guests about their first conscious reflections about the world, about life, about existence when they were youngsters, adolescents. For some people, it's kind of 9. Some people, it's more like 11 or 12. Because I think it really helps the listeners see scientists not only as the intellectual giants that they are, but also as people who were once kids like everyone else. What do you remember from that time that sticks out as significant?
I remember a big break in my thinking in the early adolescence. Before that, I was very happy, inquisitive, curious kind of kid, jumping around, running, escaping from parents, running and going to see things. Pretty sure of myself in my ways. I felt loved and the world was nice. But as soon as sort of adolescence approached, trouble started inside myself, both emotionally, but even more, I would say, as I perceived them at the time intellectually. I was confused. I was horrendously confused. And I was increasingly confused the more I sort of grew into adolescence and into the kind of thinking that, as you say, we many of us have at that time, not all of us, but many of us go through this redrawing of the universe around us. And so I started. I began to question the normal things that one questioned at that age. But then I questioned more and more and more, and habits and rules and purposes and the sense of everything and the meaning of objects and what is me and what is reality. And I literally found myself in a vortex of total confusion in which nothing made any sense. And I remember distinctively that period of my life, I don't know how long it is, because these things get also distorted in the memory, in which I couldn't say who I am, what is this? This is a microphone, this is a table, this is reality, everything was confused. I think it was very good. It was painful, because it was also emotionally and sort of, I would say, morally confusing. But it was a good thing to go through, and I think it helped in my life. Nowadays, I feel much more with ideas that seems clear to my mind. It doesn't mean that I'm particularly more intelligent at that time. Probably I was more open and more intelligent at that time. But I developed a view of the world, which more and more makes sense to me.
And perhaps in some way you built in that uncertainty, that it became part of your worldview, so it wasn't so disturbing.
That's right. That's maybe you're touching a central point here. I mean, a big part of my worldview, it is that we make a mistake if we look for certainty. And every time we look for certainty, we are opening up a trap for ourselves, for the very simple reason that we don't have any certainty.
This is exactly what we're going to be talking about in the relational interpretation, isn't it? Now, before we speak about your new book, Helgoland, which talks about this relational interpretation of quantum mechanics, before we touch on loop quantum gravity, which is your significant attempt to solve the biggest problem we have in modern physics, the reconciliation of quantum mechanics and Einstein's theories of relativity. And before we head off on the odd tangent into intuition, Buddhist philosophy, psychedelics, before all of that, I first want to deal with our main topic for today, which is this non-linearity of space and time that is so counterintuitive to us as humans, as just experiencing the world, that really sets the scene for the rest of your work. Now, listeners, you must go off and check episode 29 with physicist Paul Davies on the implications of Einstein, because he sums up so eloquently this extraordinary reality that's exposed by Einstein's two theories. And the analogy he gave, I think you're going to love this, Carlo. He said that relativity showed us that time and space were not the fixed theater in which the spectacle of nature played out, as we'd always previously assumed, but members of the cast alongside mass and energy, directly interrelating. Now, Carlo, I know you've written several books that include these extraordinarily significant implications, the most recent being your 2017 book, The Order of Time. So let's start there. Can you help us to understand how time can flow from our perspective and be measured by clocks, and yet exist simultaneously as a complete block, as predicted by Einstein's theory?
Yes. First of all, I think that the way Paul Davies put it, namely space and time are not sort of a fixed external stage within which things happen, but are actors in the game. And I think this is a very good way of expressing what we've learned with general relativity. And it's not what we've learned because we read Einstein theory. Of course, Einstein has a merit of being first who sort of understood a lot of that. But we've learned from the experiments that confirm that theory. That's what we really learned. Because when Einstein wrote this, was a great idea, but 100 years later, it's black holes, gravitational waves, expansion of the universe, a lot of real stuff out there that we're only able to understand, to think about that in terms of this space and time, which are not fixed, but are sort of interacting with the rest. You said non-linearity, non-linear space and non-linear time. Maybe it's a very maybe it's not a super precise way of expressing the idea, but let's talk about time, because time is it's probably what is more contrary to our intuition. We have an intuition of this time that it's the same for all of us. So we're all in the now, and then a moment later we're all in the next now, and then the entire universe just changes in time. Well, that's wrong. It's simply wrong. There is no sense, there's no well precise sense in which we can say what is happening now far away. What we have, it's a local time in which I am, you are, and we communicate. But even between you and me, I see you, there's some sense in the past, and you see me in the past. So we're never in the same present. And so to make sense of time, we have to think locally. Everybody has its own little time, so to say. And there's a very simple way of seeing that. It's just taking two clocks, absolutely equal clocks or watches, and it's a fact that if you have two of these and you move one with respect to the other, it's only at the first approximation that when they come back, they have the same time. If we look more precisely, there's more time up here and less time down here. So time is a local thing that is affected by what's around, by gravity, by how things move. Now, your question is about how to think about the block universe, the block time. I don't think that's a good image either. There's nothing blocky in the time. The idea of the block unit, the idea that space-time is a fixed thing that doesn't change, it's wrong, because of course it changes. It's a description of change. It doesn't change in the sense that if you think about a movie, the movie doesn't change, but it's a description of something that happens, something that change. So the four-dimensional picture of Einstein is not one in which there's nothing changing. It's one in which everything is changing, but not in an ordered way, like everybody at time one, everybody at time two, everybody at time three. There's no common time. The question you asked, how do we put this Einsteinian local time picture together with the sense of flow? And I think this is a central question, and it's a key point of this story. Time is not a single thing. When we say time, we mean a lot of different things. We mean that it's the same for everybody. We mean that it passes. We mean that the past is different from the future. All these things we take as a package, and we call time. But now there's no such package in nature, because if you move faster, some of this package is lost, but the rest remain. If you don't have a brain that remembers the past, some of this package is lost, but something remains. So to understand this phenomenology of time, we have to break it apart and say which part depends on the fact that we're just not moving fast with respect to another. So we see all clocks going at the same speed, so we get an approximation. Which part depends on our brain? Okay. You see, Freddie, when you think about time, you think about the past and the future, right? That's what you think about this line. But you're not in the past or the future. So how do you know about that? Well, because you have memory. So when you think about time, you think about your memory and your anticipation of the future. This is a key intuition. It goes back to Husserl, a philosopher, or even it goes back to Saint Augustine in the late antiquity. Augustine noticed the following: we hear the music, we hear a melody, but how can we hear a melody, given that a melody is a sequence of notes, and in any moment we only hear one note? Okay, so what we hear, it's a combination between what we hear and what we remember, and what we anticipate, because that's what music is, right? Remembering now and the future. So there's this package. Now, this package is what we call time and melody. which is something in time. But now this is because we have a brain that have memories. My clock doesn't have a memory, doesn't remember the past. So time for me is something completely different from time for the clock. So you see, there is some aspect of time that depend on the way our brain works. There is some aspect that depend on physics, that depend on the fact that we use an approximate physics because we don't know the relativity effects. Time has to be broken apart. And if you take away this part comes from the brain, this is an approximation, this is because we disregard quantum mechanics, what remains is very, very little. Mm-hmm. And in fact, we're not going to loop quantum gravity, but if you go into quantum gravity the way I understand it, in the fundamental description of the world, you don't use a time variable. There is no preferred time variable. There's change. Things happen, but they happen sort of separated and talking to one another, not evolving, as you said, in a linear time.
But what's a better word for the block then? Because this idea of the block of universe versus what Einstein called the illusory sense of past, present, and future, give us a better word for block to help me visualize that.
I think the block is a very bad metaphor. A block is something that stays there, static. The four-dimensional Einstein universe is not a block. There's nothing static there. Nothing stays there. A block is what? Is something that stays there in time, right? A block is a block of stone. A moment later, it's still a block of stone. That's what the metaphor of the block suggests. Mm. But the universe is not four-dimensionally there and stays there because there's no time in which you should stay there. So,
but my question is it that each moment in time, these discrete moments you're expressing here, beautiful analogy, the notes in music, are they all of the moments in time interrelated? Are they too relative?
They are all, each moment in time is relative to what happened in that moment of time. So
not interrelated within each other from the beginning of time to the end of time.
Oh, no. They're interrelated with each other because we know that if something happened at some time, there's something else that necessarily or most likely happened the next time. So they're not independent. But if people when people talk about the block, say, well, they all exist. They've all been there since ever. That's nonsense, in my opinion.
Now, entropy, because this is also part of this illusion of a sense of past, present, and future. Now, our previous guest, the cognitive scientist Don Hoffman, said that time in some sense can be defined in relation to entropy. Now, you make this distinction between our experience of past, present, and future, seen in nature as this inevitable dissipation of energy over time, which we call entropy, and the grammar of things at the fundamental, well, I was going to say block level, but at the fundamental time level. Tell us your take on this interesting relationship between time and entropy, and what are the implications for this persistent illusion of past, present, and future that Einstein talks about?
One of the aspects of our intuition about time is that the future and the past are completely different. The past is fixed, the future is open. We can choose the future, we cannot choose the past. We have a lot of memories of the past. We don't have memories of the future. You remember yourself kid. You don't remember yourself as an old man. Where does this difference come from? This particular aspect of time, namely the difference between the past and the future, and related to that, the sense of flow, right? The sense that the future is coming into me, or I can decide about it. The past I cannot. This moving aspect of it. This particular aspect of time, careful. What I said before is just don't make time as a single package. Time is a lot of features that we attribute to it. Now, this feature here, this difference between the past and the future, is not there in the Newton equation. It's not there in the Einstein equation. It's not there in quantum gravity. It's not there in general relativity. So, where is it? Well, it is in entropy. It is in the thing which is described by entropy, and that's a relation. That's a relation between entropy and time. The direction of time is it's related to entropy. So, what is entropy? Entropy is essentially a quantity that we can define and describe the world when we don't give a complete description, of something, but we give a blurred description of something, right? I say here there's air. I don't say where each molecule is. So it's a blurred description. So I use an approximate description of reality. And entropy, it's a quantity that counts the number of possible different ways in which, say, the molecules here can be. And it turns out that the distinction between the future and the past is the distinction between the times when entropy was lower and the time when entropy is higher. And it's not hard to, it's a long work, but it's a doable work to just show that all the distinction between the past and the future are all rooted in this entropy change, this entropy gradient, as we say in physics, this slope of entropy that is growing. So everything about time, which has to do with the fact that we have memories, that we're free to choose the future, that we remember, and etc., everything that has to do with this directionality, that's just an effect of this sort of blurring vision of time and the growth of entropy. Now you have used the word illusion.
Well, it was just it's Einstein's quote that he talks about this persistent illusion of past, present, and future. This flow that his theory has really sort of called out. I mean, I wanted to.
But illusion is a.
I mean, it means not what it seems, and I wanted to ask you: is it true to say that time is an illusion?
Einstein wrote that line in a letter he sent to the sister and the family of his best friend when his best friend died.
That gives it a bit of context, doesn't it?
Right. And it was, Einstein was old, was not far away from his own death. In fact, he died shortly. And it was a letter meant to console the family for the loss of family, and a letter in which he was talking about his own emotions for the having lost his best friend. So Einstein never wrote anything like that in a philosophical or scientific paper. He wrote that in an emotional letter consoling a sister about the death of a brother. So it has been taken in that context, as not used as an authority argument for something. But now, illusion it's a tricky word. Is a sunset an illusion? Well, yes and no. If by sunset we mean that the sun is setting, is moving down, is falling into the ocean, of course it's an illusion. The sun doesn't do anything, it just stays there. It's us sort of rotating, right? The fact that there is a sunset, is that illusory or not? Well, it's depending what we mean by sunset. If we mean the phenomenology that we see when the sun, at the end of the day, there's nothing illusory, that's real. But if we think that the sunset is the sun setting, that's wrong. Okay, so when we learned with Copernicus that the reason there are sunsets is that the Earth is rotating, right? It's spinning. So when we learned that, we're not saying, oh, we discovered that the sunset is an illusion. We discovered, well, the sunset is not sun moving down. It's us sort of, Earth is rotating, so we're moving into the shade part of the Earth because of the rotation of the Earth. So why I'm saying that, because you ask me if time is an illusion. Time is like sunset. It's a very real phenomenology, things happening around us that describe very, very well what's going on with us. So it's not an illusion, like a sunset is not an illusion. But if we think that the deep structure of reality is described by this moving time, so if we take our experience and we extrapolate and say that's the foundation of reality, it's wrong. Like if we think that since we see the sun moving, therefore for sure the sun is moving, that's wrong. We cannot take an aspect of something and make it fundamental. That's a mistake. So there are a lot of things which are not fundamental and they're not illusion. My cat, it's not part of fundamental aspect of reality. There's no cats. There are no cats in physics books. But they're not illusory, they're cats, right? And so time is time. We live in time. Time is real, perfectly real, but it's not part of the fundamental, of the most elementary structure of reality that we understand. It's not something we can extrapolate in the way we understand it generically. So, for instance, the distance between the future and the past, it's very real for us, but it's not universal. In a situation in which the entropy is constant, there's no distinction between the future and the past.
Right. Okay. Well, thanks for the clarification there. Now, obviously, it's slightly less controversial because it's less counterintuitive. But if time should be considered as starting from the individual perspective rather than from something fixed throughout all of the physical world, then what about space? And until speaking with Paul, I hadn't really thought about the implications of the extensions of objects in space also being relative. Now, obviously, we don't experience this directly as much because we don't live near a black hole or near an enormous sun or something that would really start to compress objects. But help us to understand this, Carlo. Is space and therefore matter in space also non-linear like time?
Oh yes, definitely. In a very specific and technical way, even. We have all gone to school and learned Euclidean geometry, right? The triangles and then we use the Cartesian coordinate, x, y, and then this defines space. So we have this idea of space like linear thing, something very structured. So a plane is just a plane. We are in a three-dimensional space, which you can imagine with a grid, x, y, z, etc. Well, that's not the way space is. Just space is not like that. Is it surprising? Well, is it really surprising? Look, think about the Earth. Forget the space, just the plane on which we walk. Okay. So first approximation, the Earth is flat, right? It's a plane, it's linear. But we have learned that it's not, it's curved. If you kept walking one direction, you walk, you come down the other direction. All right, so nothing surprising. It's just, like walking on an orange, you go around. So surface of the Earth is curved. Well, the space in which we are immersed, the three-dimensional space, is very much the same. So the idea that has this linear structure. So if you go one direction, you can go forever. It's just wrong. It's very possible, for instance, that in space, we could take a spaceship and fly in one direction. You fly, you continue, you come back the other side because space is curved around. And it can even be locally curved. So it might be, for instance, that in this, I make a little sphere here, and inside the volume is much more than what would it be in flat space, in linear space. And in fact, that's what a black hole is. A black hole is it's a little surface, two-dimensional surface. And you say, okay, suppose a surface is the radius is 1 kilometer. Well, inside, more or less, there should be 1 cubic kilometer less of space. No. Black hole is it's a surface with an area of 1 kilometer, and inside is a big space. Okay, this is because space is curved. Is that surprising? Well, first time that it's surprising, very surprising. But then you learn, right? It's like imagine you're a little ant that walks on a parking lot and think that the universe is flat, but then one day you see a hole and you go inside, there's another huge thing inside. Oh, okay, the world is not just so simple, there's more structure.
Which way round is it, Carlo? The closer to the speed of light I get, the larger I get? Is that right? Or is it the other way around? The more compressed that an object becomes, the closer to the speed of light?
Compressed in the sense that if you see something flying very fast, you see it shorter.
Interesting. So in theory, if
careful, you keep viewing yourself at the same size all the time.
Well, yeah, of course, yeah.
Whether you move or don't move, that doesn't matter for yourself. But if you go very fast, I mean, Freddie, you're quite thin. But if you were running very fast, I would see you even thinner than what you are.
But I guess these effects, we only really experience them at very, very large scale, very, very high speeds, correct?
Yeah. At our usual scales, they are real, they exist. but they're nearly impossible to measure. But there are many things that move fast. I mean, in physics experiments, it's normal to have particles that move very fast. In the cosmos, there are things that move super fast. Near the center of our galaxies, there are even stars that move a spectacular speed, close to the speed of light. And this is something very, very solid now. It's very solid science. It's not speculation. Things moving fast generate all this expansion and contraction of space and time.
Fascinating. Now, Carlo, moving on.
The point, Fred, if I may, is that we should not rely on our intuition too much. Okay, intuition is good. There's nothing wrong with our intuition, but we should always remember that it might be wrong. So something that seems obvious to us, we should be open to question, and science has advanced by questioning things that seemed obvious.
Exactly. Okay. Now, in my opinion, Carlo, it's no surprise that you've been so fascinated by this relativity of all these variables, including space and time. It's no surprise to me that this is how you've gone on to interpret also quantum mechanics, namely that things can only really be understood in relation to other things and not in and of themselves in a universal way. Now, this relational interpretation is the subject of your new book, Helgoland. Now, we have a detailed episode, listeners, episode 2 with John Butterworth from the Large Hadron Collider in UCL on the wave-particle duality. For anyone who wants a full analysis of that all-important starting point for quantum research, a massive explosion in physics that just completely set us off on a path that we have still yet to resolve. But Carlo, talk us briefly through the extraordinary results of the Copenhagen experiments and this mathematical probability matrix that the young Heisenberg developed to describe those results on this blustery island of Helgoland in the North Sea that you so beautifully describe in your book.
You're right. You're right, Freddie. Space and time being curved, and Einstein understanding of space is enormously surprising, but quantum mechanics is much more surprising. It was a much bigger discovery about nature. Nature works in ways that are remarkably far from our intuition, in a much more radical and violent way. And in a sense, Einstein general relativity, it's once you study it, you go into it, you start using it, everything is clear. It's crystal clear. There's nothing, it might be hard to explain, digest, and get used to, but that's it. We have understood that about the world. Maybe we'll understand more in the future. Quantum mechanics is not like that. It's so mind-blowing for the scientists. And the scientists still have the sense that they're not grasping it all the way through. And all this started exactly 100 years ago, 98 years, 1925. It was a period of a lot of confusion about experiments with atoms, spectra of atoms, chemistry, all this atomic development of atomic theory in the beginning of the 19th century. And something was understood, but not really. And something was some new equations worked, but not always. And then it was a big moment of mess in fundamental physics. And then this young kid, 23 years old, Werner Heisenberg. This is the opening of my book. It's a story of him. He goes alone in this island, Helgoland. Helgoland is the title of my book because I tell this story. In this island in the Northern Sea. And there he has an extraordinary idea and makes an extraordinary calculation. And it just changes the history of our understanding of reality. He was alone. He was suffering from hay fever. There was a strong allergy. That's why he went there, because in the island there are no trees, so the air is clean. He could breathe. So his doctor said, go away, there are no trees. So he goes there in solitude and is completely inside this question of how the atoms work. And he comes out with a mathematical game that it's what we call today quantum theory, or at least the core idea of a mathematical game that was developed shortly after by his group. In fact, Niels Bohr, Jordan, Dirac, It is what we call today quantum theory. And the key point is that he says, look, we should not describe what the atom does, what the electron in the atom does, how it moves, where it is, the force. We should not change that. That we understand. It's just an electron with an electric attraction to the nucleus. That was already understood. But we should understand totally the way we think about that. We should not think about what happened there. We should only think the way the atom affects whatever is around. Okay? What I observe about it, how I see it. But not because it has to do the mind or consciousness, nothing to do, no consciousness here, no mind. But I'm external to the atom. So anything which is external to the atom, how is affected by the atom, that's what his mathematics describe. So instead of describing how things are, it describes how things affect one another. Instead of describing how things are in isolation, describe how things are in relations to one another.
Why a probability matrix, Carlo?
Right. And the key step is that instead of saying the electron is here, is here, is here, is here, is here at every moment of time, what you say is, well, at some point I see the electron here, and at the next time I look at it, I can calculate the probability of where the electron is. Okay? So nature is not deterministic. The past doesn't determine the future. Exactly. It only determines the probability of the future. Big surprise. Well, it's not such a surprise. I mean, careful. Determinism, it's a recent idea, right? In our civilization, all civilization. In the past, nobody expected the world to be deterministic. So it was with Newton and Laplace and 18th century physics that somehow classical mechanics is deterministic. If you know sufficiently well the present, you compute as precisely as you want the future in principle. In practice, no. Well, it turns out that's not true, because if you go to small things, this determinism is not there. There is a margin of uncertainty about the future or even the past. There's a margin of uncertainty about the knowledge of reality, whatever precisely you measure something at some time. Even if you know maximum possible information about what happened at some time, you just cannot. So the probabilities. But probabilities of what? Probability of something happening? Well, probability of the system interacting with something else in one way or another. So it's a completely new way of thinking about reality, because instead of thinking about reality as a collection of things, each of which has some properties, I don't know, velocity, energy, angular momentum, you name it, which was the old way, the old physics way. This is new. So you think a collection of entities, but this entity here has property only when it interacts with something else. When it doesn't, it has no properties. It's like there's nothing to say about it. And so the wave-particle duality that you mentioned can be understood as a way to say this, what I just said. Namely, what is there is a particle, not a wave. Every time you see an electron, we see a particle. We never see a wave. But if you see the electron here, you see the electron there, in between there is nothing. There's no trajectory of the electron. And one way of thinking about it is a probability wave. There's a probability diffused in space. So in that sense, it's a wave. It's all over. And the next time you see, the wave is not real, because when you see it here, the wave disappears there. So we shouldn't think that the wave is real. We think that the wave is just our lack of knowledge of where it's going to interact with us next.
It's a probability distribution.
It's a probability distribution. Nothing else a probability distribution. Like, we give a probability distribution all the time. I mean, what's the weather tomorrow? Well, it's a 50% chance of rain. Or, if you are in London, UK, there's a 70% chance of rain. If you're in Italy, it's less. So we're used for probabilities. There's a probability of this to happen, probability of this to happen, because we don't know. So probabilities are a way of quantifying our ignorance, but ignorance is not total. Is that we don't know at all. If you say that there is 80% chance of rain, you know something. You better take your umbrella.
So tell us the problems we solve by looking at this probability distribution of quantum phenomena in terms of their relations with other things, sort of entangled phenomena we might talk about, rather than something in and of itself. something universal.
Yeah. So what happened is that Heisenberg came out with this way of doing calculations, and it was rapidly formalized by Dirac, as I said, Max Born, and Jordan, and it became quantum theory. It became what is called quantum theory. So instead of having equations that say how things move, you have equations about how things interact. And now these equations are very general, so you can apply to everything, and it basically could replace, in fact, extend the Newton equation. And it was spectacular, like it has been spectacular with general relativity. In a few years, a huge number of phenomena that were incomprehensible before suddenly became comprehensible, computable, and you can make predictions. Let me just give an example. Chemistry. We all know that chemistry is based on 100 elements which have some properties, right? And I don't know if everywhere in UK, in Italy, in the elementary classes on the wall there is the table of all the elements, the 100 elements, right? Each element has hydrogen, oxygen, iron, whatever, carbon. Every element has a certain number of electrons, atoms. Where does this structure come from? Bingo. Quantum mechanics just predict it. You make a little calculation, you can do when you're a university student, you do it, and you find exactly from the basic equation of quantum mechanics that if you take protons and electrons, you put them together, that's what come out. That's the possible shapes that can come out. So we have understood chemistry. Fantastic. And all follow with one equation. Write one equation and there's all chemistry is like. We have understood how the sun works. We have understood how galaxies form. There's new technology, lasers come out of that. Semiconductors, the basic junction in the way our computers work is computed with quantum mechanics. All small things, photoelectric things, the things that open and close the door, automatically is understood with quantum mechanics. So nowadays, quantum mechanics is really everywhere. It's as a basis of and we know that classical mechanics, old Newton mechanics is just wrong, or the Maxwell equations alone is just wrong. We can measure the discrepancy between reality and those equations. Use quantum mechanics, no, everything fits perfectly into the quantum mechanics predictions.
I guess I was thinking more about the problems raised by physicists. So the problems that we've been trying so hard by these various interpretations of quantum mechanics to get a clear sense of the way reality works. Which problems do the relational interpretations solve where the many worlds or the general Copenhagen interpretation might fall up? Why have you fallen on this side of the camp?
Yes. So we're in a strange situation with quantum mechanics because, as I said, the theory works spectacularly well. And when we use it, you want to compute a new computer chip, you use the hardware, you use quantum mechanics, it works, period. And it works in the way I said. It doesn't tell you what happened exactly. It says, I do that, that's probability for this coming out. So you can take it as it is, and not ask any question. And some physicists do that. It's perfectly legitimate. Or you say, well, wait a minute, what is really going on here? Is it really, really, really that there's nothing happening when there's not the interaction with something else? Or maybe I'm missing something? And so people try different interpretations, different way of viewing this. Some scientists say, well, maybe quantum mechanics is just wrong, and it's so funny only because it's not coherent, and the real theory is much more reasonable. And so we can change quantum mechanics and imagine that there is something more tricky going on, and we can test, and people are making test experiments to see whether these modifications, which look more reasonable, are right or wrong, and so far they all turn out to be wrong. Or you can try to make a story, fill up what we don't see. And there are two ways in which people try to fill up what we'll see. One is a many world, okay, in which the uncertainty of quantum mechanics, the uncertainty about the future, is reinterpreted as the idea that there isn't just the world we see around us with system having certain properties, but it's a collection of infinite similar worlds, plural. In each one, things are different. So quantum mechanics tell me if I throw a particle here, there's a probability goes here, probability goes here, probability goes here. Okay. Now these people think, well, maybe there's one world where it goes here, one world where it goes here, one world where it goes here. And the reason we cannot predict is that we don't know which one us will be in the next world. Because to do that, you have to think that yourself, there are copies of yourself, one yourself in each world. Some scientists think that this makes more sense. I find it baroque, redundant, and not necessarily to understand quantum mechanics. There are other ideas around. Who's right? Well, it's hard to, or possibly impossible to make an experiment to decide. So the only thing we have to do is to keep discussing, see what are the advantage of one way of thinking thing, or the advantage of the other way of thinking thing, and wait for the development of science. Because let me go to a central point here, Freddie. This is important. Science is not just about writing equation and predicting numbers. It's much more subtle, the way science works. Science is about how you conceptualize reality, how you think about reality. And let me give you an example. When Copernicus understood that the Earth is not the central universe, right? Before Copernicus, the dominant idea that Earth is the central universe, everything goes around it, sun, planets. Copernicus said, no, it works much better. It was not his idea, it was an older idea, but he took this idea, made it work very well, and he said, everything works much better. We think that the Earth is spinning on itself, okay? So it's not static there, it's spinning and it's going around the sun.
It was Bruno, right? And he died for it, if I remember correctly.
Yes, this was one of the one insisting on that. It died. But the idea is even ancient, goes back to antiquity.
Oh, really?
Oh, yeah. Aristarco di Samo had this idea.
Fantastic. I'll reference that.
Already, yes. It was known in the Renaissance. So when Copernicus did that, let's pose a hard question. Can we prove that the Earth is not the center of the universe? Of course we cannot. It's not something you measure where you're the center of the universe or not. Can we measure whether the Earth is rotating or not? No, we cannot, okay? You could still think that the Earth is the center of the universe and everything rotates once a day around and the sun, in addition, makes its own turn. You can't think like that. You don't decide between the two with an experiment. So why do you decide between the two? Because one of the two makes sense to do. Newtonian mechanics is a conceptual structure in which everything goes in order much better. Look, it was much simpler with Ptolemy, right? The Earth is the Earth, and then there are the skies. The skies it's the sun, Venus, Mars, the stars. Okay, it's very simple. Okay, Copernicus is much more complicated. The sun is a thing by itself. The Earth, it's a thing together with Venus, which makes no sense because Venus is a little dot in the star, and here is full of mountains and stuff. And the moon is still another thing, completely different. And the other stars are still something different, like the sun, but they look like. It's just more complicated. But it works. It works infinitely better, right? Because it allows us to put everything in order, write the Newton equation, and it gives a conceptualization of the world, which makes sense. So much makes sense that now we have all digested it, right? For you, it's normal to think that the Earth belongs to the same class of thing as Venus and Mars, not the sun. Well, before Copernicus, people thought that the sun belonged to the same class of things as Venus and Mars, and not the Earth. So you've changed your way of thinking reality. We keep changing the way we think reality, right? We're not starting in that. We learn. When you're a kid, you think that the universe, the real organization of the world is that you, your family, and then there's everybody else. And then you realize that it's a little bit more complicated than that. It's just one of the many.
But this conceptual framework that you're describing, which is the sort of language of science, it's perfectly represented in the problem in quantum mechanics, where we have the mathematics, we have the technology, we have everything that shows that this is the way it is, but we don't know what that means. come back
Exactly.
to relational interpretation, because you've excluded other interpretations and you've come quite firmly on the relational interpretation. Why is it so? Sorry, I'm going to use the word parsimonious. Why is it so? Why is it Occam's razor here? Why do you prefer it?
Why is compelling? Why is interesting? I think this is the right. Because I think it, no, here parsimonious is a good expression here. I think that we can make sense of quantum mechanics and we get a better understanding of nature by thinking that the Earth is not the center of the universe. We get a better understanding of nature by understanding that properties of things are relational. Properties of things pertain to how they affect something else. And this is a hard to digest idea. Like, the Earth is moving is hard to digest idea, but it puts everything in order. While if you pile up ontology, you think there are other words or the hidden variables, in my opinion, I may be wrong. In my opinion, I think I'm convinced, but I know that I might be wrong. But in my opinion, you're sort of staying hanging on a classical way of viewing reality, which was just natural for us because our brain developed for running in the savannah after the gazelle. It didn't develop for think about atoms and galaxies. So of course we things seem strange to us, but our brain is very flexible. That's what characterizes us species. We are incredibly flexible species. We haven't just run after gazelles in the savannah. We went out of Africa. We built houses and civilization. So our brain is very flexible. It can reconceive reality in different ways, and every time it does that, it becomes more effective, more powerful. I mean, sometimes we also build nuclear weapons, so it doesn't always go right.
As often in quantum phenomena, there is a cost to your approach, which you talk about in the book. There's a cost to all of these approaches, most of them, as you say,
right.
ontologically inventive. But the cost in your approach is that there are no universal facts about the world as a whole. Yeah. Only facts within entangled relations. Now, what are the implications of this cost for our scientific attempts to discern universal laws about the world? I mean, first of all, what are the implications for science? But also you as a philosopher and a scientist, like how do you find peace with that built-in uncertainty?
That's a great question. Alfredo, thanks for this question. It's fantastic. I find peace exactly in this idea that our obsession with final truth, certain certainties, getting to the bottom of everything once and for all, it's illusory. It's a dream. It's a silly dream. Okay. It's like, the little kid who wants to become the emperor of the world. I mean, forget about that. You've got to have a fantastic life without being the emperor of the world. In fact, a much better life.
But it's also your existential crisis as a teenager. It's like, I know, I experience right now that I will never reach that level of truth, understanding. And in terms of this theory, that is literally because things are only definable in terms of their relations to other things, as opposed to a single law for all things. I mean, that is a wonderful realization. Surely that in itself brings a sense of acceptance and peace, but not for the hard scientist.
I think also for the hard scientists, because it's far from me for saying that we cannot understand things better. In fact, I kept saying, we can understand things better. We can solve problems. We can ask why these things happen, and it happened for this reason. I just describe how the strange complexity of chemistry, all these incomprehensible properties of the atoms, were just all condensed in a single equation. Fantastic. Does this mean that this is the truth, the final equation, the bottom line of reality? No, it means that we've understood something more. Okay, which is what happened in our life, right? I mean, I come to know people, I know some more about them, I know more about them, become friend, I know a lot of things. Do I know the bottom line of his soul? No. Do I want to know the bottom line of soul? No, because I don't think there's a bottom line of his soul. I think there's a complexity, and I can understand more and more. I can simplify, and you look, science, physics, just forget science, just physics, haven't got to the end, right? We don't know quantum gravity. I mean, I have a theory of quantum gravity, but it hasn't been experimentally verified yet, so it may be right or wrong. We don't know what dark matter is. Plenty of things we don't know. We don't know why entropy was low in the past and high in the future. So there's plenty of things we don't know. We don't even know exactly how thunderstorms work. You know, the science of thunderstorms is incomplete. It's not clear exactly what happened in thunderstorms. There's plenty of things we don't know. Now, is going to be understood everything in the future? I strongly doubt. Should we worry about that? No, given that I'm certainly not going to understand everything. I love the fact that we can understand more, and the joy of discovery, the joy of walking beyond the hill and looking something completely new and say, wow, look, I mean, I didn't know there was this incredible plain here with a forest, waterfall. Wow. And discovering quantum mechanics and discovering general relativity. This is marvelous. We learn, we can do things, we become a little bit wiser, perhaps, certainly more capable of doing things. But that has nothing to do, in my opinion, with the silly pretension of having got to the bottom of things. And what does it mean to go to the bottom, to ultimate law? I don't know.
And there's a scientific arrogance to think that you might be able to, because, of course, with every theory, with every formulation comes assumptions, and it's coming from a particular perspective. So as soon as you place that in a different context or take a different perspective, you're going to see things differently. There's a certain sort of humility to this, isn't there? Now, I've got to ask you about this, Carlo. The way you describe it in the book, that things can only be described in terms of their immediate interrelationship with other things, it really reminds me strongly of the Buddhist concept of dependent origination, that nothing exists independently, that all things arise dependent on other things, which depend on other things, which depend on other things, and so on, in an infinite regress of interconnected causation. Now, it's a strange question, but I wanted to ask you, have you ever had direct insight or experience into that kind of way of seeing the world? Or have you only come to this through experimental data?
I've come to this only intellectually through the studying physics, which is based on this experimental data, and then reading about philosophy and thinking about the philosophical readings I've gone through. And at the same time, this sounds natural to me. In fact, the Buddhist notion that you referred to for me was important, and I in my book I have a chapter about Nagarjuna, the main philosopher in the Indian Buddhist tradition, which for me was very clarifying, and is connected to what we were saying before about certainty and about the bottom line and about fundamental description of things. When I thought hard and developed relational quantum mechanics, I was looking for a philosophical anchor background on which to put this. And of course, there's a lot of similar things in the Western tradition. I mean, there's Hume, there's Wittgenstein, there's skepticism. There's a lot of there's all the relationalism of Leibniz, of other. There's process philosophy. There's a lot of that, but there was nothing that really seemed sufficiently radical to be a philosophical basis for the ideas that seemed to be necessary for understanding quantum mechanics. And then I stumbled on Nagarjuna. In fact, I stumbled on Nagarjuna because people kept telling me, I mean, you should read Nagarjuna if you think this way. And then people said so many times that to me that I said, oh, okay, I got to read Nagarjuna. So I read the main book of Nagarjuna. It's a wonderful translation by Garfield. Joe Garfield, which is it's a great analytical philosopher who studied Buddhist philosophy, and it just shocked me. It's just fantastic. It's a beautiful, beautiful, beautiful philosophical work, which I find extraordinarily convincing. And what it does, it's all negative. It just demolishes things. The entire book demolishes things. And it demolishes things precisely by showing that nothing stands by itself. But in a way that doesn't throw you into confusion, like I was in my adolescence, nor into silence, because it leaves open to the possibility of talking about things, just standing on one another. So it's not that because we lack total certainty or we don't understand the foundation that we cannot do science, we cannot understand things, we cannot. It's not because I don't know the depth of your soul that I cannot talk to you in an interesting and meaningful way, which is good for me and for you, and we learn, and it is real. Okay, so you don't know the foundation. This deep anti-foundationalism of Nagarjuna, which is wonderful for me. He has this notion of emptiness, right? Emptiness is exactly it's a technical word in Buddhist philosophy. It's exactly to say the thing is empty doesn't mean that there is no thing. The thing exists, but it means it doesn't exist just by itself. If you forget what is around it, you don't know what you're talking about anymore.
Form is emptiness, and emptiness is form, right?
Exactly. And Nagarjuna is fantastic, and then it shows how everything is empty. And then in the moment in which you're tempted to say, okay, I got it, the bottom of reality is this emptiness, it tells you that emptiness is empty. And then at that point you fall in love with him because you say, yes, I mean, this. It's like Wittgenstein. It takes away from you a false problem, in a sense. For a scientist, it's absolutely marvelous. Now, I know, and somehow your question maybe hinted to that. I know that Buddhism is not just an intellectual exercise. It's a practice, and it's a way of it's an internal path. I'm not a Buddhist. I have a lot of sympathy for Buddhism from many grounds, but I'm not myself Buddhist. I don't practice anything related to Buddhism. So in that sense, for me, this has been an intellectual relations, not else.
The reason I ask about the direct experience rather than the intellectual path is because with Paul Davies, we spoke about Einstein's praise of intuition. And Einstein is quoted to have said, intellect has little to do on the path of discovery. There comes a jump of consciousness. Call it intuition or what you want. The solution comes to you, and you don't know how or why. Now, we spoke about how Paul had often experienced something similar. He gives it a hilarious example of him doing the cryptic crossword. And he said that sometimes he can't get the answer even by sort of bludgeoning his way through intellectually. And later on, out of nowhere, the answer just comes to him. And he doesn't know from where. And he certainly hadn't worked it out intellectually. So that was kind of the scope of my question. Have you ever experienced altered states of consciousness? I don't know, for example, mystical experiences or meditative states, deep intuitions, psychedelic experiences, these jumps of consciousness that Einstein's talking about, in which you appeared to access information about the way the world worked in a kind of non-intellectual way? And if you have had these experiences, how did it change the way you saw the world?
Yeah. So the answer is yes. Let me elaborate, because it's two different yes. So let me start from the way science works, and then go to the personal experience. It's a complete misconception to think that science is about just making measurement using mathematics and being rational. I mean, this is the most irrational things of all. The rational thing is the checking, is not the getting ideas. Okay, but the getting ideas is not marginal; it's the main thing. So, to find new ways of thinking, to find a new take on a problem, to make this step is what every scientist, I'm not talking about, Einstein, the moment in which he conceived general relativity, I talk about everybody who is in science, especially in theoretical science, but I believe experimental science is the same. I mean, you don't know how to do something, and then, yeah, I have an idea how to do this. Ideas come like that. Oh, yes. Oh, yeah, I could do that. My main idea came from, driving to school, walking in the forest, taking a shower, and then the way it works is that you get your mind into a problem. You keep reading, working, you do calculation, you know it. Just you walk on the boundary of knowledge, back and forth, back and forth, back and forth. And it seems as there's just no way to go the other side. It's just doesn't work. And then at some point, you forget something, you say, oh, there's a crack here. So you go through, I found something new. And very often it doesn't work. It was wrong. You just get stuck in a hole and you cannot come out, and you have to start again. Sometimes you make some step ahead. Why? Because our brain, because that's the way our brain works. Our brain works by analogies, right? By putting pieces together which don't fit, and then taking a piece of that. Oh, look, it's fit this way. And if you think, if you really think all that step in time, they're all jumps like that. It's funny because the Eastern philosophers, the Chinese, have recognized that better than the Westerners. If you look at the whole Chinese philosophy, China hasn't developed a science like Western science. Okay, so Western science has to go to China late. But the Chinese had a reflection about how you think, which I think was more clear at some point than the Western one, because the Western attempt to formalize logic, which was fantastic, because logic is an incredible tool, and use mathematics and use et cetera. It's great and offered a fantastic tool for science. But with that alone, you can do anything. What you need, it's a mind that generates new things by analogy from all things, for jumping around, by pulling things from the air. Why? Because that's, we have all these neurons doing funny things. We have to follow the way our neurons work. The neurons don't work with logic, they work with similarities. Now, what about myself? Because you got to that. Have I experienced?
And what about altered states? What about altered states? Because those moments seem to give us a type of information which interests me a lot, because there's very clearly something coming through in these moments that we don't really have a good scientific understanding of where that information is coming from. So I'm very interested about these altered states, and there are many different types. Some of them are using external substances, some of them completely instantaneous, seemingly out of nowhere. So yes, I guess my interest is in if you felt a different type of information coming through in those moments.
Yeah, because look, I come from a generation. I'm 66. I come from a generation that experienced a lot with psychedelic drugs in the youth. So psychedelic drugs were a part of my LSD, magic mushrooms, psilocybin, mescaline. It was a part of my sort of
rite of passage.
Yeah, rite of passage, and it had a huge influence of my worldview, for deep influence of my worldview, because it was not for a long time. It was not so many times, but there were very strong experiences, extraordinary strong experiences, which affected my worldview in a way that I think left a sign. You see, I think that the brain, the way our brain works, I'm immensely interested in neurosciences, like many today, and sort of deeply and eagerly following everything that happens in neuroscience, in all the various people in school that in different ways to try to make sense of how our brain works. Our brain is not... it's a horrendously complicated thing that works in a way that we understand very little. But it's a very concrete thing. I don't believe a moment to connect to one of the other things that you treat here, that there is a hard problem of consciousness. I don't think there's a hard problem of consciousness, but I think there's immense soft problem of consciousness. What do we do in the language of David Chalmers? We understand very little how it works, but certainly one way it works is that it has a rigidity into it, which is absolutely necessary. We think we know what we see. We think we know what we know. We have clear ideas about everything around, and this rigidity saves us from the confusion of my adolescence. So allows us to do things. But this same rigidity is the one that forbids us from understanding better. So when you break this rigidity, you have chances to find a step ahead. And obviously, I mean, a psychedelic experience is a dramatic break of this rigidity. So you're invaded by experience, Huxley, right? The doors of perception so are open, and you suddenly realize that things could be seen in ways profoundly different. Your own identity, the reality of things, could be melted in something completely different. Which is not surprising for me as a scientist, because of course, I mean, why should my brain be capable of seeing reality as it is? It's not. It sees reality in one possible ways in which reality can be sort of dealt with, because we are dealing with as animals with reality. But of course, that's one perspective on reality. So the moments in which you break the strict categories and structure and logic through which you understand things are moments in which you risk to lose yourself in the sense of then, I mean, you have to go shopping and eat, but also the moments in which you open up possibilities for understanding more. So there is a balance between things. Now,
can you maybe give us an example, Carlo, of one experience that changed the way you saw the world, or that maybe influenced the way your physics went in the future?
Well, the first thing we've been talking about is the nature of time. And one of the common reports in psychedelic experiences is a profoundly altered sense of time, in which time not only sort of goes much slower and much faster, but somehow you perceive that there's no time moving at all, or things like that. You just a sense of being outside time. Now, this is, I don't have a mystical reading of that. I mean, this is a chemistry in my brain that allows me to perceive reality differently. But there's a lesson here. My usual vision of reality is also chemistry in my brain that allows me to see things in one way. So the output of that is 50 years or 40 years later, when I'm a scientist, a professor of physics, and I talk with my colleagues, and I said, look, in quantum gravity, you think you have to write this equation so and so and so, and there is no time variable because it evolves. And some of my colleagues says, oh, come on, I mean, that's necessarily wrong, because of course there's a time variable. This is obvious around us. How can you think without a time variable? It seems to me, this is my reading, that they have a rigidity that is forbidding them for accepting that there is a way of conceiving reality, which is not the one they're using. And I'm not sure, but I think that my experiences about the different way of conceiving reality in a psychedelic flight in my adolescence were part, at least, of the gave me part of the flexibility for thinking this way. And which doesn't mean, I mean, since this is doesn't mean at all that you do good science by taking drugs. It's not.
No, although there are many physicists.
You definitely don't.
No, although there are many physicists who have dabbled, and they're grateful for it, which is interesting. And listeners, do go and listen to our episode on altered states of consciousness with psychologist David Luke, and we talk about the fact that the neuroscience research shows that in all of these experiences, both for meditation and for drug-induced experiences, they see a lowering of the default mode network, which is, in some sense, the place that generates our sense of self and our sense of quotidian reality. So it's interesting, this idea that you could lower the influence of a particular rigid structure, as Carlo's putting it, this sort of rigidity, and by taking down the power of that, it opens us up to a much greater range of possibilities. Now, Carlo, I want to come back to time for a moment, because my mystical experience, which wasn't related to psychedelics, it was completely improvised. I experienced what I later found when studying religion, was called dependent origination. I experienced dependent origination not through data, through this extraordinary experience. And I experienced not only the fact that all things, things in the physical sense in the world were interrelated through this network of eternal regress of causation, but also that all moments in time were dependently originated. And that's why I wanted to come back to that question I put to you earlier, because something about the Einsteinian view of time, sort of beyond this flow, really reminded me of my experience, where I just really felt like, in that sense, both future moments in time and past moments in time were equally as interdependent on each other. Now, is this something you've come across either in your studies, or have you ever experienced something like that, or maybe even come across it in the implications of some of the equations?
Good. Yeah. Let me take this question in this sense. I'm
testing your rigidity, Carlo.
No. But let me let me take it in this sense. Yes. I recognize that an experience of that can be possible, and I think that, from my perspective, what I view in this experience is not so much the realization of how things are, but it's the realization of how one can look at things, which is crucial, because that's what science is about, is how one can look at things. And I think so I read this beautiful story that you tell me in the language of what you said before, namely as a way of sort of jumping out of a reading of reality which seems normal in our everyday life, but it's far from being the only possible one, and it's far from being the best one for understanding reality outside the domain of our normal experience. So what I'm saying is that I think that if we got a good intuition by experience, by direct experience of the world at the quantum gravitational level, the deep relativistic quantum regime, we might have a perception of reality which is closer to what you describe than the usual temporal story narrative in which we place ourselves in our everyday life.
Well, this is what I wanted to get to, this limit of science, which is probably, where most people in the arts would sort of say, okay, this is where science can't go any further. But you try and go further, and you venture a science of meaning via the concepts of information and relational interpretation. Now, I've never come across a way of establishing a science of meaning. I thought it was a subjective question.
I think we should establish a science of meaning. It's why shouldn't we decide a science of
meaning? Well, no,
right?
I'm really curious how you start. Like, where do you start from? Because surely that's completely subjective.
Yeah, but subjective things are real. That's the point. That's relational. To be relational doesn't mean to be false. Subjective doesn't mean to be false.
Right.
It's just, if my computer takes a picture of my room, what is in the bits of my computer is very subjective for the computer, right? It's not my room. It's just bits but are related to that.
So give us an example. Something really meaningful for me. I don't know, maybe.
No, wait.
Maybe a cat walks across my path or something, and I'm like, oh my God, that means something.
Yeah. No. In fact, careful, because my point about meaning is not just relations. It's more. So I think that's my contribution. I think that to understand what you mean by meaning, we have to put two things together. That's each one is wants the other one. So first of all, it's a relation. Okay. It's a relation between something in my head and something outside. Outside is a cat. In my head, there is some neurons that fire everybody every time they see a cat. Okay. Inside the computer, there are some chips that, some memory that has a picture of Freddy, and somewhere there's Freddy. Okay. But that's by itself, it's obviously not sufficient because there are plenty of relations in the world that has no meaning whatsoever, right? So I'm just said something stupid. Okay, if there's meaning, in particular, there's relation. Or what is that makes a relation meaningful? Okay, and here I think we have to go to the specific of what we are, and what we are is product of evolution. And evolution, this is the total genius of Darwin, of course, Charles Darwin. Darwin has been able to show, and convincingly, has convinced at least the intellectual world, maybe not everybody on the planet, but everybody who has a degree at least in the planet, that the finality that we see in nature is perfectly compatible, understandable, in terms of a causal process, so in terms of efficient causes, because when you have a biological system that has certain eyes, for instance, or does certain things which maximize his probability of surviving, then you have more of this. So therefore, when you find many of this, is not because you have to assume a priori an objective, but is the fact that they have this property that allows us to be such. Okay, that's the core of Darwinism. That's the central idea, which goes back, by the way, to Empedocles. Aristotle discusses this idea in his biology and attributes it to Empedocles. Aristotle disputes this idea for very good reasons, for very good arguments, but quite remarkably, it leaves a window open, because it says, look, we don't see cows coming to life with all sort of number of legs and only the 4 legs to survive. But then he talks about seeds. So he leaves open the possibility that there is indeed natural selection as a way of understanding structure and meaning and the purpose in biology. But it has to go through species, not to individual. So the idea was there, but of course it's Darwin that made it into something comprehensible and reasonable, and commits all that. But once you understand deeply exactly what is the core of the Darwin idea, then you realize that in biology, so for this particular process, which is a physical process, like many others, it's one way for the entropy to grow of the living organism. Some things are important and some other are not important. So if you have a bacterium and it's something inside itself is correlated to something else, period, well, that's just a correlation. It's not meaningful. But if there's a part of the bacterium which is correlated with a sugar outside, okay, and it determines the motion of the bacterium, then seeing the sugar is meaningful for the bacterium because it increments the survival possibilities. So biology has meaning in its core, right?
That makes sense. But what about higher order stuff? Like, for example,
exactly,
the meaning of life.
Basic.
You know, the meaning of life.
Exactly.
What would be the fitness payoff for me to, instead of go off and hunter and gather, to sit, you know, staring at my navel, thinking about the meaning of the universe?
Because you're perfectly right. So that's the basis. So I think that's what the biology gives you, a notion of meaningful, which is a biological notion. It's correlation which has an advantage. But then there is a full evolution. So then evolution itself uses this notion of meaningful, and of course our brain, our culture, it's built on itself. For me and for you as persons, meaning is not something we come from outside, right? Meaning is just we find meaning. We don't do meaning. When I'm hungry, a piece of bread is horrendously meaningful. When I'm thirsty, I mean, water is the most meaningful thing in the world. When I'm in love, that person I love is the most meaningful things of the world. The universe makes sense because the eyes of my girlfriend, right? everything is there. I mean, it's real. Why? This is what meaning is this drive that comes from inside. And the same meaning is the same drive is the one that, you know, makes me shout for justice, or I see people dying in a war and I want to do something about it, because for me, I'm personally hurt by something. And if somebody hurts me, I'm even more meaningful. So meaning is not something we have to search. in fact, it's the right way around. I think we have to compress inside of ourselves. We have too much meaning. We have too much desire, often in contradiction to one another. And a good job that our brain does is to keep things at bay, because if I let everything go, it would mess. I mean, we don't.
At default mode network again.
That's right. So, is there meaning in the universe? Well, depending on what we mean. I mean, if we mean that the stars itself, they think in terms of meaning, that's absolutely not. It's not appropriate for describing a star meaning, but it's completely appropriate to describe the way I view the star and the beauty and in terms of meaning. So the meaning is not there; it's in the relation between what is me being my chemistry, my biology, my culture, my emotions, all that, which is all real. Physics is a combination of everything.
Well, this is extremely interesting, and it's quite new for me, because I'm more on the sort of philosophical kind of thoughtful side of things, and to see this idea that even the deep meaning we find in our greatest search for the meaning of life, our deepest philosophical questions, could have an evolutionary, even quantum relational source is quite extraordinary. I think I need to shake up my rigidity this evening to think about it. Listen, Carlo, you've been so generous with your time. Thank you for going into so much depth about Helgoland. Listeners, you must go out and get it. It's a very short volume written in the keynote, extremely beautiful way that Carlo has of making everything seem very beautiful and very meaningful and very poetic. Can really recommend it. Now, just to close, Carlo, we're not going to go into it because it is a conversation unto itself. But obviously, all this work coming from the classical perspective of Einstein's relativity, and then this quantum perspective of entanglement and these probabilistic superpositions, led you quite early to tackle this huge problem of reconciling the two. Particularly with Lee Smolin, you proposed your loop quantum gravity solution. Now, if you could, not worrying too much about the maths or how it solves the problem, but just a little bit about this loop idea, because it relates back to our time conversation. What roughly is the structural concept that you're proposing to solve this problem?
Yeah, I can say just a few words. First of all, it's not in trying to address the difficulty of generativity and quantum mechanics that I moved up to quantum gravity. In a sense, for me, what happened was the opposite. I mean, as a too courageous young man, I decided to tackle the problem of quantum gravity, which is a problem of bringing together the insights of Einstein generativity and the insights of quantum mechanics. So I went into this full strength when I was a young man, and that has been the central scientific search of my life. Try to build this theory. I think that I work with many colleagues. Lee Smolin, you mentioned, is one. Vajashkar, Jorge Pooling, Jurek Lewandowski, Thomas Tiemann, many others. And now there are hundreds. Right now, the conference with 100 people. And there's this beautiful theory, which is loop quantum gravity, which I think is a tentative theory of quantum gravity. My own biased view is by far the best option we have for a quantum theory of gravity. We don't know if it is right, because in science you have to test before getting convinced, and tests are waiting. But there's no negative sign. Nothing has gone wrong so far. Everything has gone. So I view it as a possible solution. The core of the theory is just taking the core of generativity, the core of quantum mechanics together. And generativity tells us that space and time are dynamic, are things, right? They're not just a stage. And quantum mechanics tell us that these things are relational, are probabilistic, and are discrete, right? Made by little chunks. Mm-hmm. So quantum gravity, loop quantum gravity, is a mathematics that describe a chunky space, a discrete space, which behaves probabilistically, and which manifests itself in relations. So instead of having space and time as a fixed thing out there, and things move in space and time, you fold space and time, like a little bit like you mentioned at the beginning, Paul Davies said. I mean, space and time become one of the actors, but it's a quantum actor. So it's an actor that can be in a superposition. So now my clock, not only two clocks can have different time spans between the same events, but the same clock can be sort of quantum spread in a superposition between different times. It requires a little rigidity in thinking about space and time. And I think the theory is there. I'm moderately optimistic, but not sure about
and is there a reason
describing the world.
Is there a reason, Carlo, why, if the maths works, is there a reason why the majority haven't come around to your take on this? Is there something that you've noticed? Is there a particular criticism that has led to people go more down the string theory route?
Well, one reason was the great enthusiasm of string theory for a long time. I think that this enthusiasm is going down a lot. I mean, there's much less enthusiasm in string theory because of non-detection supersymmetry, because of the...
And they've put billions of dollars into testing it, and they've come with nothing. It must be very disappointing.
Oh, it has been disappointing. I mean, there were articles on major newspapers in France. I mean, a crisis of physics. It was, a crisis of physics for somebody is a success for somebody else, right? So I was very happy when supersymmetry was not. Obviously, yeah. I mean, the success of your enemy doesn't mean that your success. Not necessarily, but it was good news for us, nevertheless. Look, these things are slow, very slow. So I think it's okay. I mean, there have been long disputes in science, in the history of science, and Boltzmann struggled horrendously to have his ideas. Copernicus, for a century and a half, was not really taken seriously by the majority of the people. I mean, you had to wait for Kepler and Galileo for a century later for Copernicus to be really... So I'm not saying I'm Copernicus, not at all, of course. But the science goes slowly. This idea that science is rushing, it's silly. I mean, if you look back at the history of science, the periods are a little bit faster, a little bit slower, but understanding is slow. And when you're in the middle of things, it always looks a mess. It has always been like that. It's very rare that there is even the great successes. Look at the fantastic experimental successes the last years. The Higgs gravitational waves, the black holes, the picture black holes. It's just fantastic results, but it has taken a century for finding that these predictions were correct. And nature has been very conservative. Nature has said yes to all the conservative ideas, right? Because all this is a fantastic new science. Even the last Nobel Prize of quantum mechanics just confirmed quantum mechanics as written by Dirac and Heisenberg and company in the 30s. Just confirmed that. The discovery of black holes and gravitational waves, 2 Nobel Prizes. It just confirmed Einstein equation of general relativity written in 1915, 1917. The quantum mechanics Nobel Prize a few months ago just confirmed the quantum mechanics, and so on and so forth. So a lot of speculations, maybe the world is like that, nature has said no. Slow science, grounded on what we know, so far has worked very well. So I think that, with all my radicalism about time, about what the nature of reality, I think that the best thing we can rely upon in understanding looking in the dark is what we know well: quantum mechanics, general relativity.
Well, listeners, I'm sure, Carlo, I'm sure that many of the people listening now are already great fans of your work and may have read some of your books. Which is the right book to read if we want to learn more at a sort of public level rather than a science level about your loop quantum gravity? Is it Reality is Not What It Seems? Is that the best place to go?
Yes, definitely. Definitely. I mean, for people who know nothing about science, the 7 lessons is always a little entry into the fascinating 7 lessons and the 7 brief lessons physics into the world of science. But to know more about loop quantum gravity, the book I wrote for that purpose is Reality is Not What It Seems.
Wow. It will all be in the show notes, listeners. Carlo Rovelli, it remains for me just to thank you extremely. I'm so grateful for this elucidation of your ideas, and that I got to wax lyrical on a few of the more interesting areas of Helgeland, particularly the Buddhist philosophy part. Thank you so much for being with us, Carlo, and all the best in the future.
Thank you for having me. That was a great conversation. Thank you, Veli.
My pleasure.